Nobody has any homework questions you want me to go over? Okay. Well, the first thing I want to say is there is a type of process that we're going to see sometimes called a polytropic process. And I think you had one or two of these in your homework that's due tonight. And it's given in a form something like the pressure times the volume to some exponent is equal to a constant. Okay. And this is not based on a certain type of material or anything. This would just be for your specific process that you're doing. You've done experiments and measured that it fits this curve fairly well, or you assume that it's going to fit this curve, and you're just going to find these constants to make it match as well as possible. In order to do problems like this, so some very useful things for polytropic processes. Are two logarithm facts. The first one is, this is just a reminder, you've all seen this long ago. Natural log of two things that are multiplied together is the natural log of the first one plus the natural log of the second one. And the natural log of something to a power is the power natural log the base. Okay. So I'm going to do a couple examples of things like those. So let's assume that the pressure times the volume to the power of 1.2 is equal to a constant. And we're given that at instant 1, there's a pressure P1 of 3 bar. A bar is 1 times 10 to the 5th pascals. So this is 3 times 10 to the 5th pascals. We'll use that bar unit pretty often. And then the volume at instant 1 is 0.1 cubic meters. And then at instant 2, we don't know what the pressure is, but we know the volume is 0.2 cubic meters. And the question is, what's W for this process? Let's make that part A. And then for part B, let's say if the system is well insulated, what's the change in internal energy? Okay, so with these polytropic processes, there's either a case where you have to calculate one of those constants or two of those constants. Depending on whether this exponent is given or whether it's not. In this case, it's given, so the only thing we have to solve is for the constant. And then that'll give us enough to calculate the pressure here. Okay. And just to jog your memories, how are we going to calculate that work? How are we going to calculate W? What's our game plan here? Yeah. Yes, exactly. So the thing about these polytropic processes, they're almost always going to come up in problems where it's going to be helpful to compute that integral to calculate work. Okay? Because they let you come up with pressure as a function of volume. Okay? And remember, that's the requirement for using that work's integral. So remember, work is equal to the integral from volume 1 to volume 2 of P dV. So you can't do this if you don't have pressure as a function of volume. And that's what this gives you. Okay. So we're going to use instant 1 to calculate that constant. I'm going to keep everything in SI units here. So we have 3 times 10 to the 5th times 0.1 to the power of 1.2 is equal to C, and we can just calculate that. Punch that into your calculator and you get 18,928.7.
That's unitless.
It does have units, and you could figure out what they are because you know it has to match the units of this. So this is going to be like, oh my God, the units are crazy though. But so it's units of pascals, and then so pascals times meters to the power of 3.6. You know. So it doesn't mean anything physically, really. Okay, so now what we know is we have P times volume to the 1.2 is equal to 18,928.7. And what we're trying to get is pressure as a function of volume. So now we can multiply both of these sides by, so we'll multiply each side by volume to the negative 1.2. And that's going to give us P is equal to 18,928.7 times V to the negative 1.2. And the reason that we're doing that is that volume to the 1.2 times volume to the negative 1.2 is equal to volume to the 0, and that's 1. Okay? And now we can calculate the work. So it's equal to the integral of P dV from the starting volume to the ending volume. The starting volume was 0.1. The ending volume was 0.2. And so this is 18,928.7. I'm just using the polynomial rule for integrals. So this is now negative 0.2. And so we're dividing by negative 0.2. And then we're evaluating this from 0.1 to 0.2. plug all those in, and it gives you that the work is no, it's not negative, positive 19,417.4 joules. Does it make sense that the work is positive? That is based on a rule that you should keep in mind because it's really helpful for stuff like this. Anytime your system expands, the work of expansion, W, is positive. Anytime your system contracts, the work is negative. This is going from a volume of 0.1 to 0.2, so we know it needs to be a positive work.
Can you say that again, please?
Yes. W, if your system, the gas that you're isolating, expands, then W is positive. Okay? If your system contracts, W is negative. It's like think of a piston in a cylinder. If the gas expands, the piston rises, and that does work on the surroundings, so W is positive. If the piston goes down, the work is compressing the gas, and so the surroundings are doing work on the gas.
Thank you.
Yeah. Okay, so that's W, and the next question is, if the system is well insulated, what's the change in U? Well, we know that the first law says the change in system energy is equal to heat Q minus W. If the system is well insulated, there's no energy being exchanged because of the temperature difference at the boundary, and so this goes away. Well insulated always just means that there's no heat transfer. Our delta E is the change in kinetic energy plus the change in potential energy plus the change in internal energy. If we're not told otherwise, we're always going to assume that kinetic energy and potential energy are roughly constant. And so we have that the change in internal energy is equal to negative W. And so it's negative 19,417.4. If the internal energy is reduced, either the temperature goes down or or you're in the middle of a phase change from a higher state to a lower state. So like this could either make the temperature go down or it could make a gas go towards being a liquid.
So assuming it's well insulated, your delta U is always just going to be the opposite of W.
That's right. Yep, that's right.
And it's negative because the energy is leaving the system?
That's right. Correct. So remember that what W means is the work done on the surroundings by the system. And so negative means that, no. So positive W, like we had there, means that energy is going from the system to the surroundings. So our system is losing energy.
Because the volume got bigger, so it pushed.
Right. That's right. Okay, let's do another one like this. So during a process, we know that pressure is equal to A times volume to the B. And we know that 200 joules of heat is added to the gas. At instant 1, the pressure is 2 bar. And the volume is 0.3 cubic meters. And then the process happens, and at instant 2, the pressure is 0.5 bar, and the volume is 1.5 cubic meters. Assuming that there's no important change in kinetic energy or potential energy, what's the change in internal energy? This is almost exactly like the last problem. The form of the polytropic process is, that it's presented as a little bit different. Instead of P times V to something, it's already given as P as a function. And then there's one more difference. In the last one we did, there was one constant that we had to solve for. In this one, there are two constants. And notice what you need additionally as givens in a problem where you're trying to solve for two of these constants. In the first example, we were just trying to solve for one constant, so we only needed a matched pair of position and volume at one of those two instants. We didn't have it at instant 2, right? In this one, since we have two constants we're trying to solve for, we need the two matched pairs, okay? Because you need a system of equations that's the same number as the variables you're trying to find. Okay, is W going to be positive or negative in this case?
Positive.
Positive, yep, because the volume's increasing. Okay, so let's come up with our two equations and solve this system. We know that 2 bar, or 2 times 10 to the 5th pascals, is equal to A times 0.3 to the power of B. I am going to write that as, so I'm going to use the exponent, the logarithm rules. Natural log of 2 times 10 to the 5th is equal to the natural log of A plus B times the natural log of 0.3. And so I'll just write this for now as natural log of A is equal to natural log of 2 times 10 to the 5th minus B times the natural log of 0.3. Set this equation aside. And now we'll go to instant 2. That says that 0.5 bar, so 0.5 times 10 to the 5th, is equal to A times 1.5 to the power of B. And so natural log of 0.5 times 10 to the 5 is equal to natural log of A plus B times the natural log of 1.5. And I'll write this as natural log of A is equal to natural log of 0.5 times 10 to the 5 minus B times the natural log of 1.5. And the two boxed equations are our system. So we can set the two right sides equal to each other. So we have natural log of 2 times 10 to the 5th minus B times the natural log of 0.3 is equal to the natural log of 0.5 times 10 to the 5 minus B times the natural log of 1.5. And now we can just calculate these. Let's see, did I do it the same way? Probably not. So natural log of 2 times 10 to the 5, that is 12.206 minus so the natural log of 0.3 is negative, so this comes out to be plus 1.204b. And now the right side, natural log of 0.5 times 10 to the 5th is 10.820 minus 0.405b. And so we get 1.609b is equal to negative 1.386. And so B is equal to negative 0.861. And so now you can go to any equation you have up here to calculate A. I'm going to go 0.5 times 10 to the 5th divided by 1.5 to the power of negative 0.861. And so A is equal to 70,889.9. Okay, so now we have those two values. We can come up with our function P as a function of V. So P is equal to 70,889.9 times volume to the negative 0.861. And so W is the integral from our starting volume, 0.3 meters cubed, to our ending volume of 1.5. Of P dV and so that integral is 70,889.9 times V to the power of 0.139.
How did you get that value?
Which one?
0.139.
Oh, I'm just taking the integral of this, so I just added 1 to the exponent, and now I'm dividing by this new exponent. You know, it's the same thing as the integral of x squared is equal to x to the third divided by 3, but with fractions. And this is evaluated from 0.3 to 1.5. And I get 539,568 minus 431,409. And so the answer is positive 108,159 joules for the work. Everyone following the thought process so far? Okay, it didn't ask for that. It asked for the change in internal energy. And we're given that there is 200 joules of heat added. So now we're going to go to the first law of thermodynamics. Bless you. We know that the change in kinetic energy plus the change in potential energy plus the change in internal energy, and these two, we're told that those are 0, is equal to Q minus W. So the change in U is equal to, 200 joules of energy is added through heat to the gas. So is Q positive 200 or negative 200?
Positive.
Positive, yep. Q is the amount of energy added to the system. So this is 200 minus 108,159. And so negative 107,959 joules. Negative is the change in internal energy. So since the gas expanded, we knew that the work was going to be positive. We knew W was going to be positive. And we knew that positive W means taking energy away from the system and giving it to the surroundings. Heat was added to the gas, so that would increase energy, but it was the magnitude of the heat that was gained was much smaller than the work that was done on the surroundings, and so we ended up losing net energy for the system. Okay. And I really think it's a good idea for you to, as you do these problems, just think through the meanings of all those things to kind of train your brain about what does it mean when W is positive? What does it mean when Q is positive? What does it mean when internal energy is positive or negative? Okay, just think that stuff through. Any questions about that? It's a lot like the last problem. The math gets more complicated because you have to solve that system of equations, but that's all. The trickiest part of this is dealing with the logarithms and stuff.
Is that pretty much the kind of the standard format of these kinds of questions?
For those polytropic processes, dealing with the first law of thermodynamics, they're kind of all the same. The only thing that's different is whether you're solving for one variable or two.
And then whether or not it's insulated or there's some sort of heat
That's right.
transfer.
Yep.
And that heat transfer in these problems anyway is going to be given.
The heat transfer, yes, in a problem like this, it'll be given. Pretty soon we're going to get into some ways of calculating heat transfer. But really, I'd say for most of this class, either the heat transfer is going to be given, or it's going to be the thing that you use the first law to solve for. So one thing that's going to be pretty common is, for now, this internal energy is just kind of like this black box thing, but we're going to start using property tables where we'll say, okay, the gas we're dealing with is like a hydrogen gas or whatever kind of gas, and we know the temperature and we know whatever, and that's going to let us look up the internal energies. And so internal energy pretty soon is going to be something we're going to be able to figure out, and then we'll be able to solve for the heat.
So really, you're just kind of opening up new variables.
Yeah.
Still the same.
Right.
Overall problem.
Yes, and that's exactly what you want to get to is yes, every problem looks the same. It's just where in this whole flow are you plugging in things you know? Yeah. Okay. One more example problem. This one is not polytropic. Let's do this one. Okay, so let's say that we have a cylinder and a piston. And the piston has a mass of 5 kilograms. That's a big piston. And the gas inside is our system. And we have 1 kilogram of gas inside this cylinder. And it goes from a volume of, so this is actually a specific volume. So it goes from a specific volume lowercase v1 of 0.5 cubic meters per kilogram to a specific volume v2 of 0.3 meters cubed over kilogram. And the area of the piston is 0.02 square meters. We're going to assume that atmospheric pressure is 1.01 times 10 to the 5th pascals. And there are two questions. First, what's the pressure in the gas? And second, during this process, if the cylinder is insulated, what's the change in internal energy? Okay, I know there was at least one question like this on the homework that's due tonight, where you have to calculate the pressure based on forces acting on the piston. In this case, there's no extra external force, but the force acting on the piston is just the weight. So if this is an equilibrium, I'm going to draw a free body diagram of the piston. So this is just like a side view. And the force is acting on the piston. There's a weight force down of 5 times 9.81, so 49.01, 0.05 newtons. Okay. And then there are two other forces acting. One is the force pushing down on it from the atmosphere. So that is the atmospheric pressure times the area of that cylinder. And then the other one is the pressure of the gas pushing up on the piston. And so that is the area of the piston times the P that we're trying to calculate. So Newton's second law for equilibrium says we can add up all the things pushing, let's just call one positive and one negative and write it like Newton's second law. So pushing up, we have 0.02 times the pressure. And then negative, I'm going to call down, so we have minus 49.05 and minus, what do you get if you multiply these? (2020). Equilibrium says this is equal to 0. And so 0.02 times P is 2069.05. And so the pressure is 103,453 pascals. Or if you want to compare it to that atmospheric pressure, that is 1.03453 times 10 to the 5th pascals. So a little bit bigger than atmospheric pressure. Okay, well, as this process happens, the force acting on the piston is constant, okay? So this pressure has to be the same through this whole process, okay? It wouldn't be the same during instance if this was like a really fast process, but if in most cases we're going to assume that equilibrium is basically held through the whole process. So you can think of this process as happening slowly and this piston slowly moving. That's called quasi-equilibrium. And that just means, yeah, it's basically in equilibrium the whole time. Stupid computer.
If what?
If the cylinder's insulated during this process, what's the change in value?
Okay, so what that's going to let us do is that's going to make this integral to calculate W really easy because the pressure has to be this the whole time. Okay. So P is constant during the process. Okay, so work is equal to the pressure dV from the starting volume to the ending volume. The starting volume is 0.5 cubic meters. Oh, no, I got to be careful here. So this is from V1 to V2. Now I did this one by giving us the specific volume to sort of try to point out that you got to be careful. We're integrating here with respect to the actual volume, and these boundaries have to be an actual volume. So if you're given specific volumes, you need to change that to actual volumes before you do that integral. Okay? So our V1.
Yourself up with your own trick.
Yeah, exactly. Right, exactly. Yeah, life's exciting when you can't remember anything, you know? Like everything's a surprise. So this V1 then is going to be the specific volume times the mass, and it would have worked out fine in this case because I gave a very boring mass of 1 kilogram. And then V2 is 0.3 times 1. And so now we can compute that integral.
And that was the mass of the gas?
Right. Yep. So from 0.5 to 0.3 of 1.03453 times 10 to the 5th dV. Do we expect this work to be positive or negative? Yeah, negative because it's contracting in this case. And so this is 1.03453 times 10 to the 5th times 0.3 minus 0.5. And that is negative 20,690.5 joules. Now we'll go to the first law. These two we're going to assume are negligible, and that is equal to Q minus W. It's insulated, so there's no heat transfer, and so the change in U is equal to positive 20,690.5. And so the effect is the gas is compressed, and compressing a gas raises its temperature, and you see it there in the change in internal energy. Any questions about that problem? Okay. Well, over the weekend, I'm just going to give you a bunch of first law problems like this. And then we'll get into some different forms of the first law on Monday.
And we would be able to calculate like a certain change in a temperature scale.
Yes. Right now, obviously, we don't have a way to do that. But if you have if the gas is a type of material that's been mapped out in functions or for us in tables,
Specific heat.
you can do it. Or if it's if you can treat it as an ideal gas, then there's ways to do it using the ideal gas law and related things. So a lot of what we're going to do in this class is how to deal with different materials to figure out, once you get to this point, what else can we say about the properties of this gas.
So in those tables, are they just experimentally defined?
Well, yes, a lot of it is experimental, but then the entropy stuff and the enthalpy stuff, I think, that are in those tables are actually just calculated using more complicated differential equations than what we're doing in this class.
They just like model scenarios.
Yeah. Right. When we get to entropy, like way down the road, like entropy is a very kind of theoretical thing. Like there's no entropy measuring device, you know. But temperature, pressure, specific volume, that stuff is all experimental.
Cool.
Yeah.
Wouldn't it just be like a dial set to max?
What?
Entropy?
What's that?
Like maximum.
Oh yeah. Yeah, entropy is cool. That's like when we get to entropy, this class will all of a sudden turn into like philosophy.
Cool. Full circle.
Yeah.
Reading a book right now about the history of calculus.
Oh yeah, really?
And it's super exciting. Yeah, it actually is really cool.
Have a good weekend.
You too. Bye.
So,